Today we're going to be talking about quadratic functions. We're going to talk about the vertex, which is either the highest point or the lowest point on a parabola, which is the graph of a quadratic function. We're going to talk about the line of symmetry, where it's symmetric across it, meaning that it folds on top of itself. And we're also going to talk about how to know whether it opens up or down and how to get it into what we call the vertex form by completing the square. So I'm going to go ahead and share my window with you so you can see more easily what I'm writing, but you'll still see a small window of me up in the corner. Let's get started. Here we go. So let's just start by talking about what is a quadratic equation. What does it look like? Now, we've seen these before, but now we're looking at them as specifically functions. So let's remind ourselves what a quadratic equation is. So remember that a quadratic equation typically looks like ax squared plus bx plus c. Now, it's a function, which means that when you draw a vertical line, it only intersects the graph one time or not at all. In the case of a parabola, it will always intersect it because the domain for a parabola that opens up or down is all real numbers. In other words, all values of x will get used, but not all values of y. Now, the reason for this is that a parabola looks like this. So it's sort of a U shape, which either opens up, or in this second case, we'd say it opens down. Now, there is a point that is either lower than all the other points on the graph or higher than all the other points on the graph. And that point is called the vertex. So this is the vertex right here. And of course, the vertex serves as both a maximum on a downward opening parabola and a minimum on an upward opening parabola. So we have a point that is a maximum or a minimum. You know, there are lots of times we want to maximize or minimize things. So we'll often be looking for that point, which is the vertex. Now, it's also symmetric to itself. Now, my picture notwithstanding, there is a line that goes through the middle. This line is called the line of symmetry. Now, we're going to be studying parabolas that open up or open down. Now, these become functions because they pass the vertical line test. You take a vertical line and you move it from the left to the right across the graph. It never touches the graph more than one time. If it touched it twice or more, then it would not be a function. Now, we do have parabolas that are not functions. These would be ones that open sideways. So here's an example of one that opens to the right, and there's the vertex. But you can see that it is not, in fact, a function because it touches the graph twice with a vertical line. Now, we're going to be focusing again on functions, which means we can use function notation. So when we use function notation, instead of writing y equals ax squared plus bx plus c, the typical quadratic, we're going to write f of x equals ax squared plus bx plus c. Now, it's important to know whether it opens up or down. I mean, there's a big difference in the pictures. So how do you know? What's the value of a? It's very, very simple. If a is positive, it opens up. If a is negative, it opens down, with up being the positive direction and down being the negative direction. So in this case right here, we know that a has to be strictly positive, and here we know that a has to be strictly negative. You may say, well, what if a is 0? Well, if a is 0, we don't have a quadratic equation anymore, right? We have a line. So a cannot be 0. Can b be 0? Yes, it can, and it would still be a quadratic. C could also be 0, and it would still be a quadratic. It would still look like a parabola, either opening up or opening down. Now, this line that goes through the middle, where it's symmetric, this is called the line of symmetry, right? So when we talk about the line of symmetry, we're talking about a line that goes through the vertex where the parabola will actually fold onto itself. Now, it's also true for parabolas that open left and right, but they're not functions, and we're not going to focus on those. When we look at the ones that are functions, this would be the one on the left, what you see right here, and the one on the right, what you see right here, ignoring this guy. So when we're looking at these, the line of symmetry goes through the vertex. So we want something special for the vertex. So what we've done is we've called the vertex HK. So the point of the vertex is the coordinates HK. Why H and K? Well, because they're not used very often for other stuff, and so they were available. I mean, there is no reason why. So we have HK as the vertex, and this would also be HK. Now, what we want to do is we want to decide what the line of symmetry is. Now, it's a vertical line, so you know it has the equation x equal a constant. All vertical lines have the equation x equal a constant. In this case, it goes through the vertex, so it has to be that x coordinate. So the line of symmetry then becomes x equals h, right? So it's always going to be the coordinate for the x coordinate that gives us the line of symmetry in a quadratic function. Now, what do we need to do? Well, we need to talk about what they're called the vertex form. Sometimes it's called standard form, not instead of general form. This is what I would call general form right up here. Sometimes the vertex form is called standard form. I don't really like that name. I tend to call it the vertex form. So what does the vertex form look like? Well, in the vertex form of the equation of a quadratic function, so I'll write vertex form here, we have f of x equal to a times the quantity x minus h squared plus k. Now, it always confuses students. Why is it minus with the x and plus with the k? Why aren't they both minus or both plus? Well, the simple reason is h affects horizontal, right? H is the horizontal component of the vertex, and it's sitting right next to the x, so it's a minus. Now, the k actually affects the y value, but notice that the y value is replaced with the function notation f of x. If we put the k over here with the y, where it sort of belongs, it would also be y minus k, and then we would have this equation right here, and they would both be minus. But again, that's because it would be sitting next to the variable it affects. But most of the time we want it solved for y, which is why we tend to use this equation right here. This is called the vertex form. Now we need to talk about how to get it into the vertex form. You'll notice that a right here is still the a coming up here from the general form. It's the same a. But in the vertex form, what we see instead is we see that we have x minus h, where h is the x coordinate of the vertex, quantity squared, plus k, where k is the y coordinate of the vertex. So in order to get it in this form, we have to complete the square. I had a video on how to complete the square, but I'll go through it again just to make sure that you know what you're doing. Let's go ahead and take a look at our first problem, which is a more simple problem. Now, more simple doesn't mean simple. It's more simple than ones where a is not 1, but that doesn't mean it's simple. In fact, I consider completing the square to be quite difficult. So let's go ahead and take a look at that and see how to proceed. So you can see right here that we're looking at section 5.1. This is problem 1 out of the OpenStax Algebra and Trigonometry 2nd edition book. And when we're looking at this, we have the function f of x equals x squared minus 2x plus 6. Now, the first thing to notice is that a right here is not written, but it's understood to be there. It's the number 1. It is positive, which means that this has to open up. It's an upward opening parabola. Now, this, however, does not represent h and k. We want to get it into this form right here. So what we're going to do is complete the square. Now I'm going to go through the steps, the same steps that I would go through if a was not a 1, so that you have sort of one process to fit all situations. So we're going to start down here with f of x equal to x squared minus 2x plus 6. Now, the first thing you would do is if your a was not a 1, you would factor it out of the first two terms. Leave some space and then write the +6. Notice I did not take the a out of the constant. I only take it out of the x squared term and the x term if the x term is present. Now, in this case, 1 factored out leaves these numbers unchanged, but if this wasn't a 1, this coefficient and this coefficient would be different. This coefficient would become a 1 because I'm going to take out a, and this coefficient would be whatever the original b divided by a is. So this right here actually becomes b divided by a. Again, we're talking about that general form, ax squared plus bx plus c. Now what we're going to do, so what we have right here now is we've got 1x squared minus 2x. Now we're going to complete the square. We're going to force a round peg into a square hole or a square peg into a round hole, however you want to think about it. We're going to take this number right here, which I call capital B. It is not lowercase b necessarily because that comes from general form. In this case, they're the same. But our capital B is actually equal to lowercase b over a. So we're going to take our lowercase b over a, and we're going to take half of it. So we're going to take 1/2 of b over a, which is going to give me 1/2 of -2, which gives me -1, right? Now, when I factor this, I'm going to have a -1 in the binomial, guaranteed. I forced it to fit a pattern. Now, before I do that, what I'm trying to build here is what's called a perfect square trinomial, so that when it factors as the same binomial times itself, a binomial square. So the next thing I want to do is I want to take half of this b over a, and I want to square it. So this would give me -1 squared, which would give me 1. I'm going to take this 1 that you see right here, highlighted in yellow, and I'm going to add that number in here. So whatever that is, when it's squared, that's what we add inside of our trinomial, and I've left some space to do that. Notice that it will always be positive because I squared it, so that's not an issue. Now you can factor this trinomial, and it will always factor, guaranteed, and it will always factor the same way. So we still have our a outside, which in our case is a 1, and then it's going to factor, and the number that we have, let me get another highlighter here. This number right here is going to end up going in here, including the sign. So whatever we got when we took half of lowercase b over a, this is the same thing inside the binomial square, exactly the same. Now you may be saying, well, what about that +6 over there? Well, it's still there, all right? So we still have the +6, but we also have a problem. What's the problem? I added 1 in here that was not originally in the problem. I've changed things, right? And am I allowed to do that? No, I am not allowed to do that. So what I'm going to have to do is I'm going to have to compensate for adding 1 by subtracting 1. So what I've done is I've basically added 0. Am I allowed to add 0? That I am allowed to do. I'm allowed to do 2 basic things. Add 0 anywhere, anytime I feel like it, and multiply by 1 anywhere, anytime, whenever I feel like it. Those 2 things we're always allowed to do as much or as little as we want. Adding 0 does not change the problem. Multiplying by 1 doesn't change the problem. So how do I compensate for this -1 that I've now put in right here? Well, I'm going to take the a and I'm going to distribute it over this -1, my compensation term, and I'm going to put that out here. So I have 1 times -1, which is in fact -1. Notice that the first 3 terms went into my binomial square, and now I've got this -1 plus 6. So I'm going to go ahead and rewrite it. So here's my a, here's my binomial square, and -1 plus 6 is 5. So what does that tell me? Well, that tells me that it opens up because A is positive. It tells me that the vertex is 1, 5. Remember, it's always opposite next to X and the same as K because K is not sitting next to the Y. That's why it's a plus and not a minus. So our vertex then becomes 1, 5. And our line of symmetry becomes X equals 1. Remember, that's a vertical line that goes through the vertex. Now let's go ahead and graph this on Desmos so we can see what it looks like. So I've gone ahead and graphed it for you. You'll see the equation for it right here on the left. And you can see that it plotted itself here in red. I don't know why they always use red for the first one, but they always do. Now, notice that the vertex, which in this case is the minimum value, is going to be this point right here. Now, how do I get that point? Well, notice that's 1, 5. That's the lowest spot. That's what we got for the vertex. And the line of symmetry goes through it. It's X equal 1. And if I wanted to graph X equal 1, I could do that. And you'll see that it makes this line right here. And let's go ahead and make it a dashed line. And you can see that the parabola is symmetric across this line and that they both go through that point 1, 5. So this is what it looks like when you graph a quadratic equation and when you look for the vertex by completing the square. Notice that the vertex here is the minimum value and the line of symmetry is going through the vertex. Now let's talk briefly about domain and range because we're going to get into some problems that talk about that. Remember that the domain is all the X values that the function can use, and Y is all, or range is all the Y values that the function can use. Now, when you look at this graph, notice that it tilts outward to both the left and the right. So eventually, it's going to keep reaching left and right. It's going to use up all the values on the x-axis, which means the domain of this is all reals. Now, what about the range? Notice that the parabola is going to continue going up to the left and to the right, but it never goes down below the y value of 5 at the vertex. So that means that our range has to be from 5 to infinity and including 5. So over here, we're going to write down that the domain is going to be all reals, which would be negative infinity to infinity. And the range is going to start at the number 5 and go up. So again, we write it in number line order. So the 5 has to be on the left and the infinity has to be on the right because that's the order they go in the number line. And again, what we're looking at right here is we're thinking about a number line. Here's 0, here's 5. We're including the 5. That's why we use a square bracket, and we're going to the right. And there's the 5 on the left and infinity on the right, 5 on the left, infinity off to the right. Let's take a look now at our next problem. But let's take a look now at this particular problem. We have f of x equals 6x squared plus 12x minus 4, and we want to put it in the standard vertex form, a times quantity x minus h squared plus k, where hk gives the coordinates of the vertex, not negative h, just h. So the first thing we need to do is complete the square. And when we complete the square, the first thing we want to do is we want to factor the a out of the x squared term and the x term. So we're going to take the 6, oops, erasing while I'm writing, and this becomes 1x squared in parentheses plus, and again, this is like a 12x divided by 6. And so this gives us, in effect, 6 times x squared plus 2x plus some stuff minus the 4. Now notice everything is happening on the right-hand side. I'm going to keep everything the same by adding 0. So what do I need to do? Well, I need to take that b over a. So remember, this was b and this was a. So I'm going to take that b over a and I'm going to take half of it. Well, b over a is the number 2, so I'm going to take 1/2 of 2, which gives me, of course, the number 1. So when I factor it into a binomial squared, it's going to be x plus 1, absolutely guaranteed. And then to find what to add in the trinomial to make that happen, I'm going to square that half of b over a that I just found. And when I square 1, I still get 1. So I'm going to add 1 in here, but to compensate, I'm also going to subtract 1. We call that add 0. So right here, what I've done is add 0. All right, so the next thing we're going to do is we're going to factor the first 3 terms into the binomial square and distribute the 6 times the -1. And what I say is bounce it out of the parentheses. So now we have 6. The trinomial, the first 3 terms, factor as x plus 1. Notice that this one right here matches what's inside of the binomial, and it is squared. And then we're going to take the 6, and we're going to multiply by the -1, and then we're going to write it right there. So 6 times -1 is a -6 minus 4. So cleaning up the 2 constant terms, the next thing that we're going to have is 6 times x plus 1 quantity squared minus 10. Now we're ready to go ahead and pick off the vertex. So A is 6, which is positive, which means that it opens up. So it's got to look something like this. And we want the vertex. So we're going to find the vertex. Now remember, the vertex is HK, and the formula here is x minus h. Now this doesn't have a minus in it, so how do I deal with that? Well, I can make it a double negative. So this would be the same thing as writing 6, x minus a -1 squared minus 10. So this right here becomes my h. So the vertex becomes -1, -10. In other words, you use the opposite of the number that is inside the parentheses, and you use the actual number that is outside the parentheses. So opposite of the one sitting next to x, the same as the one sitting on the outside. And that gives us our vertex. Now our line of symmetry would again be x equal the x coordinate of the vertex. So this becomes x equals -1. And because it opens up, the vertex has to be a minimum on the graph. Now, what about our domain and range? We know that it has to look something like this right here. It has to open up, and we know the coordinates of the point at the bottom have to be -1, -10. So it uses a y value of -10, and then it goes up. So again, the arms spread out forever. So eventually it uses all x values to the left and to the right. And so we know that our domain is again going to be all the real numbers from -infinity to infinity. But our range, because it opens up, is going to start at the y coordinate of the vertex, -10, and go up, which would be towards positive infinity. So we have -10, infinity. Let's take a look at the next problem. So let's take a look at this third problem. Determine whether the function 7x squared plus 14x minus 6 has a minimum or a maximum value, and find the value of the minimum or maximum. Okay, now the minimum or the maximum is the y value at the vertex. Where it is the x value. The actual minimum or maximum is the y value, k, in other words. And then they want us to find the axis of symmetry. Well, we know that for a parabola, the minimum or maximum is always at the vertex. So what they're really doing is they're really saying, find the vertex, and then for the minimum or maximum, give the y value there. That's the min or max. And then find the axis of symmetry, which is the vertical line that goes through h. So it's x equal h. Okay, Pretty simple, right? Yeah, not at all. So what we're going to do is we're going to do this two different ways, all right? There are two ways to find the vertex. One is the method that we just done, and since we need more practice, let's go ahead and do that right now. So we've got the function f of x equals 7x squared plus 14x minus 6. Now, I'll warn you that completing the squared, this is really nicely set up, but it often leads to fractions, all right? So I know it's not our favorite, but just you're going to have to deal with it. All right, so first thing we're going to do, factor a out. Now, remember, factoring out is just a form of division. So that's 7 divided by 7 and 14 divided by 7. So this gives us 1x squared plus 2x. Leave some space in there for our added term and then the subtracted compensating term. And then we have the minus 6 sitting over here. Now, again, we know that this value right here is actually b divided by a. So b divided by a is 2. Now we want to take half of that. So half of 2 is 1. And then we want to square that. And these are always the same steps. So b over a is whatever happens after you take a out, and you take half of it. That's what goes in the binomial squared. And then you square it. That's what you add and subtract in the trinomial. So when we square 1, we still get 1. So we're going to add 1, and then to compensate, we'll subtract 1. The first 3, we're going to factor. It's always going to give me x, and then whatever this is, sign included, is going to go inside the binomial square. Now I have to compensate for what I did there by bouncing this guy out of the parentheses, and 7 times -1 is a -7. Then we have minus 6. So we can write 7 parentheses x plus 1 quantity squared minus 13. Now remember, the formula for the standard form, the vertex form, is a quantity x minus h. We don't have a minus. So we can rewrite the plus as a double negative. So this becomes 7. Sorry, my dog's going nuts. Hang on a second. So you can see that I've replaced the plus sign with a double negative. And now I know that I can write the vertex down. The vertex is going to be at -1, -13. Now let's go back to the problem. Remember, it's asking for the minimum or the maximum value. So the minimum or maximum value is going to be the y coordinate. So the x coordinate gives you, oops, I erased it. All right, the x coordinate gives you the where, and this gives you the max or the min. So we've got to decide, is it a maximum or a minimum? Well, let's go back to our equation and look at a again. A was 7, which is positive. So since a equals 7, which is positive, I know it has to open up. Well, just look at the picture. It's got to be a minimum. So in this case, our minimum value is -13. That's the smallest y value that gets used. Okay, now it also asks for the line of symmetry. Remember, the line of symmetry is basically x equal h. So our line of symmetry is going to be x equal -1. Now, I said I was going to show you 2 ways to do this. So, and what we've done right here, what I want to come back and look at right here is look at this right here, and let's kind of imagine, what does this +1 represent right here? This +1 is half of b over a. Now, that's a positive one, but what we need is actually the opposite of it in order to get the x coordinate of the vertex. So if I took -b over 2a, that would be the x coordinate of the vertex. So this is another way of solving the problem. So let's rewrite our problem again. So I'm going to create a bar here so you don't mistake one section for another, and I'll write in a different color. So we have 7x squared plus 14x minus 6. I said, by looking at what we did with completing the square, that the x-coordinate of the vertex has to actually be this middle part, but the opposite of it. So instead of half of b over a, it's negative half of b over a. So this is going to give me negative b over 2a, or half of b over a with a negative on it. Now, I can find this directly without completing the square, which lots of students like this part, without completing the square by looking at the original equation. So my original b was 14. So I take the opposite of b, so I make it negative 14, over 2 times a, which was 7. So I have negative 14 over 14, which reduces to negative 1. That is exactly what I got up here previously for the x-coordinate of the vertex. Now you may say, yeah, that's great, but you got to get that minimum value since it opens up, and you don't have that. When you use this formula, you only get the x. That's true. But we do know it's a function. And I know that if I take this value of negative 1 and I substitute it in place of the x-coordinate in the original equation, I should get the y value when x is negative 1. So this is going to give me, well, negative 1 squared is 1, so that gives me 7, negative 14, and then minus 6. So negative 14 minus 6 is negative 20, so I have 7 minus 20, which gives me negative 13. And that's exactly what I got previously. So this is the way to find the coordinates of the vertex without completing the square. Now, the way that you want to do it is probably totally up to you. Certainly in my class, it's up to my students, whichever method they prefer. In order to use the formula, it has to be in general form, ax squared plus bx plus c. That's one drawback. But again, completing the square does take a fair amount of work, so there are some drawbacks there as well. Let's move on now to the next problem. In our next problem, which is problem number 4, we want to repeat the process, but notice here that we have a negative 3 as a. This is going to change some things, so let's work on this problem next. So let's go ahead and work this both ways so that you have practice at doing both. So the first thing we're going to do is we're going to rewrite the problem as is so that we're starting from scratch. This is always a good idea in case you mistakenly get a different number somehow. That way your instructor knows what you're starting with. So the first thing we want to do is we want to factor out the negative 3. Now we know when we factor the negative 3 off the negative 3x squared, we know that's going to leave behind x squared, but yeah, taking the negative 3 out of 12 can be a little tricky. So what we'll do instead is we'll simply apply the division rule, and we're going to do the 12x divided by negative 3. That's what it means to factor something out. And we'll leave some space, and then we have our minus 2. And then we're going to reduce so that we have x squared minus 4x, leaving space, minus 2. So that means that our b divided by a turned out to be negative 4. Now we need to take half of it. So we take half of b over a, which gives me a negative 2. And then I'm going to square that value. And when I square the value, I get 4. So I'm going to add 4, which changes everything. So I got to compensate by subtracting 4. So because I add 4 and subtract 4, I've added 0, which means I haven't changed it. I'm going to take the first 3 terms and factor them as a perfect square trinomial. It's going to be a binomial, and I guarantee you that I'm going to have a minus 2 in it. So it's going to be x minus 2. And then I'm going to bounce out the compensating term. So this is going to become x minus 2 quantity squared, where these minus 2's match up. And then I've got to bounce this guy out. All right. Now, some students like to go ahead and just write it so that they make sure they don't mess up the signs. So we have a negative 3 times a negative 4, which is going to give us a positive 12. So this is going to give us negative 3. x minus 2 quantity squared plus 12 minus 2, which is going to give us a plus 10. So we have negative 3, x minus 2 quantity squared plus 10. Now let's go back to the problem and remind ourselves what we're looking for. It says it has a minimum or a maximum value. We want to find the value of the max or the min, and then find the axis of symmetry again. The value of the maximum or minimum is the y-coordinate of the vertex. So our vertex here is going to be opposite of what's sitting next to x, so 2, and exactly what's sitting outside the parentheses, the 10. So our min or max value is 10, but is it a min or a max? This time, a is negative 3. So since a is negative 3, which is less than 0, we know that it has to open down. And that means our vertex is a maximum. So our maximum value is 10. And then our line of symmetry is going to go through the x-coordinate of the vertex. And so our line of symmetry has to be x equal 2. Okay, let's take a look at the next problem. So in problem number 5, we're asked to find the domain and the range of a quadratic function that has already been put into standard form. Now, how do we know it's in standard form? First off, the coefficient of the x in the parentheses must be a positive 1. If it's not actually standard form. And then we notice that it is in parentheses with something added or subtracted to it, and it's squared. This 10 that's sitting right here must be a. So we've got a equals 10, which is positive. So we know it opens up. That means that our vertex is a minimum value. So all the y values are that number or bigger, right? And then we want to determine what the domain and the range is. Now we know it looks like this, and remember the arms do go out forever, which means that eventually it uses up every number on the real number line. So the domain that we have right here is definitely going to be negative infinity to infinity, as it is with all up and down opening parabolas. Now what about the range? The range is going to start at the y value at the vertex and move up. So our vertex, we've got to find the y value of the vertex. So when we're looking here in our standard vertex form, remember that the x-coordinate is the opposite of the number sitting next to x because it's right next to it, so it's minus. But the y value is on the opposite side of the equation. If we moved it to the left where y is, it would be minus 3. But because it's on the opposite side of the equation, we can just use 3. And so that means that the minimum y value has to be 3, and then it gets bigger from there. So make sure you write it in number line order, 3 on the left, infinity on the right, and use a square bracket for the 3 to show that you're including it. It is a part of the parabola. Let's take a look at the next problem. In this problem, we have negative 5x squared plus 20x plus 3. It is not in the standard vertex form. Now we want the domain and range. Now we know the domain is going to be all reals because it either opens up or down. And because this one has negative 5 for a, it has to open down. The only problem is the range. We need to know the y-coordinate of the vertex. So what I want you to do is pause the video and either complete the square to find the vertex or use the formula. The x-coordinate of the vertex is negative b over 2a or negative half of b over a. And then find the y-coordinate by substituting that value back into the function. So go ahead and pause the video and turn the video back on and we'll compare our answers. So how'd you do? Did you get it right? I hope that you did. So let's take a look and see what we've got here. So on the left in blue, I went ahead and completed the square, first factoring out the -5 and taking b over a, which became what I had after I factored out a, which was -4. Half of that is -2, but when I square it, I get +4. So I added 4 and then compensated by subtracting 4. The first 3 factor as the binomial squared x minus 2 quantity squared. And then I bounce out the compensating factor by taking a -5 times a -4. Now, when I combine all of this, I ended up with the vertex of 223. Now, this problem is a little different than the ones we've looked at in the past. A is -5, so it's negative, which means that it has to open down, which means the vertex is the highest y value. No y value above that ever gets used. So in this case, when we're looking at the range, it's negative y values, so -infinity up to 23 and stop. Notice the -infinity is on the left, because if we were to graph this on the number line, like this, then what we're talking about is somewhere there's a 0 and somewhere out here is a 23. We're talking about using 23 and all the negative numbers and the numbers between 0 and 23. So it goes to the left. So this is -infinity to 23 on the right. Now in the gray on the right side, you'll see I use the formula half of -b over a, or -half of b over a, or -b over 2a, however you want to remember it. That gave me the x-coordinate of the vertex very quickly as 2, but then I have to substitute it into the function to find the y value. And this is where it can get a little difficult. Make sure when you do this that you follow the order of operations. Square it first, right? So no matter what number is in there, it's going to end up positive because you're squaring it. And then you multiply it by a. So in this case, because a is negative, that first term is always going to be negative. And then go ahead and simplify the rest of it. And again, we get the vertex is 223. Okay, let's take a look at another problem now. Now, this is a different type of problem, what we're seeing right now. So what we're looking at is we want to find the general form. So general form is f of x equal ax squared plus bx plus c. Everything multiplied out, not the standard vertex form. A times quantity x minus h squared plus k. So we're not looking for that one. We're looking for the ax squared plus bx plus c one. And this time they give us some information. The vertex is -1, -1, and we have a point on the graph. Now this point on the graph is not the vertex, it's just some random point. So what we really know is we have these 2 points and we want to fit a vertex through them, which sounds a little sketchy to me. So let's graph what we've got so far and see what it is that we're trying to do. So we have -1, -1, and -5, 15. So let me open up another Desmos window and we'll plot a point. So we can plot -1, comma, -1, if I can find all my things. All right, so we have -1, -1, and the other one was -5, 15. Okay, so this becomes -5, comma, 15. All right. Now that's way off the screen, so I'm going to scroll in a little bit so I can see where it is. All right. Now some of you may go, oh, well, obviously it's a parabola that opens up, right? Yeah, not necessarily. Or is it? Look at this. Which one of these was the vertex? Let's go back to the problem again. The vertex is -1, -1. We don't know if that's a min or a max. But now we've got this point which is above it, which means that it can't open down, because if it opens down, the vertex should be the highest point. So this must, in fact, be a vertex or a parabola that opens up, and it must look something like this. In fact, I could even find another point on it, right? I could count over. This is 1, 2, 3, 4. So there has to be a symmetric point on the other side of the x-axis. 1, 2, 3, 4. So it has to go through the ordered pair 315 as well, right? Because it's symmetric across that line of symmetry. How can I get the general equation? What we're going to do is we're going to use that standard vertex form. So we're going to write down the standard vertex form formula, a times x minus h quantity squared plus k. And we're going to go ahead and put in the h and k value that we know. So we have now f of x equal to, now I don't know a, but I know that h is a -1. Notice that that gives me a double negative. The minus is a part of the formula, but h itself was also negative. So I've got two negatives. Don't mistake one for the other. And then the k value was -1. So this becomes a -1. So I can rewrite this as a times x plus 1 quantity squared minus 1. Now, that's all great, except I don't have a. What I do have is I have a point that's on the parabola, which means when I plug it in, it must create a true statement. So I know that f of -5 has to give me 15. So if this is 15, when I plug in -5, then over here, I should be able to replace x with -5 plus 1 squared minus 1. And that would give me everything except a. And then I can solve for a. So remember order of operations. We have to do what's inside the parentheses first. So this is going to give me 15 equal to a times the quantity. -5 plus 1 is a -4. And then I'm going to have to square it first. So that gives me a 16. So I have 16a minus 1. And then I'm going to add the 1 to both sides of the equation, keeping it balanced across the equals. And I get 16 equals 16a, which tells me that a is 1. And then I can rewrite it in the vertex form, starting right here. Let me use a different color. So I got a equals 1. So this tells me that my function is 1 times x plus 1 quantity squared minus 1. Now, that's all great, but it asks for the general form. Oh, such a pain. All right, so what are we going to do? First order of operations tells you you square it first. And I find for most students, it really helps to write it out. It actually saves you time. I know students have this idea that the more you write, the slower you are. It's actually the reverse in college. The more you write, the faster you are because you're freeing up your brain to do the hard thinking and keeping track of the details on the paper. Write more, think more. All right, so then we're going to do a binomial square using the FOIL method. So this is going to give me 1 times x squared for the first. The outside is a 1x, the inside is a 1x, and the last is a plus 1. And then I still got my minus 1 over there, kind of running out of room. So when I distribute the 1, it doesn't change anything. So this is going to give me x squared plus 2x plus 1. That's the perfect square trinomial that we tried to create, right? And then we've also got this minus 1. Notice that the plus 1 minus 1 cancels, and I get x squared plus 2x, which is what they're looking for. That's the general form. And you may say, oh, God, I wouldn't want to complete the square on that. That's no big deal. You don't have a constant term, so just write plus 0, right? That's the same thing. So it would be fine, and you would do just fine on it. Let's take a look now at the next problem. Well, before we move on, we probably should go ahead and look at the graph on Desmos and see if, in fact, it did go through our two ordered pairs, and you can see that it did. I put in the general form, x squared plus 2x here, and it's going through our vertex at -1, -1, and through the point that we were given -5, 15. So we have that point as well. Well, if I can get it there, it doesn't want to get right on it, does it? Okay, well, there it is, -5, 15. Okay, let's now take a look at the next problem. The next problem is very similar. In fact, it's exactly the same as the previous one. They give us the vertex, they give us a point, and they want us to determine the general form of the quadratic equation. So this time, try it on your own, all right? So don't forget, we're going to be using the general standard form or vertex form. So we have a times x minus h quantity squared plus k. So go ahead and plug in h and k, get an equation, and then go ahead and plug in the point to find the value of a. Then turn the video back on and we'll compare our answers to each other. I don't know why they're giving you such simple A's. They should give you something harder. So maybe on your homework, it will be more difficult. When you're looking at this one, again, you're going to use that vertex form, the standard form for the quadratic function. And when you plug in the values of the vertex, notice that the x coordinate goes after the subtraction sign, and the y coordinate keeps whatever sign it has in the vertex. So this is a -4. And then we know that f of -5 is 45 because the point -5, 45 is on the parabola. Now we don't know if this one opens up or down because we haven't done a yet, and we didn't plot it, so we don't have a clue. So this time I went ahead and did it without plotting it. So I substituted -5 in place of the x coordinate and 45 in place of the function value. This gave me -7 following order of operations squares 49a, move the 4 to the other side by adding it, and that gives us that a is a +1. And then we can go ahead and multiply this out, and we end up with x squared minus 4x, right? And so then you can, of course, be sure, make sure that it did work out. If I put -5 in here, -5 squared is 25, and minus 4 times a -5 would be a +20. So 25 plus 20 is in fact 45. So it does work, all right? And then you could also check to make sure the vertex is on here as well. Let's take a look now at the next problem. So let's now look at problem number 9. Most of problem number 9 is exactly what we've been doing, so it's not any different. It says find the vertex, the axis of symmetry. And here's the different part, and the x-intercepts. So remember, an interception in football is when the opposite team gets the ball. The ball in this case is 0. So if you're looking for an x-intercept, y has the ball, meaning y is 0, right? So an x-intercept, the x coordinate may or may not be 0, but the y coordinate is 0. In other words, this is where it touches or crosses the x-axis. So let's kind of take a look at a couple of the ones that we've already plotted. You'll see that in this upward opening parabola here, it does cross the x-axis twice. One of them is here at 0, 0, and the other one is there at -2, 0. So we're looking for those x-intercepts, the places where the y coordinate is 0, but the x coordinate may or may not be. But again, the y has to be 0 for an x-intercept. Now, how are we going to do that? Well, if we know the y is 0, then we are in essence solving a quadratic equation set equal to 0. So we just take this x squared plus 4x minus 1, set it equal to 0, and solve. Now, you already know multiple methods of doing that. We can complete the square and solve. We can use the quadratic formula. We can factor and use the zero product property. But there are occasions like this one that might cause us some problems, because this is an upward opening parabola where the vertex, of course, is right here at 1, 5. And if the vertex is there and it opens up, and never crosses the x-axis. So what's that going to give us when we try to solve it? Well, what it gives us when we use the quadratic formula or completing the square is it gives us something with the square root of a negative number, which is a number and does exist. It just doesn't show up on the real number line. So it's not a real number line number. It's an imaginary number, which does not mean it doesn't exist. Imaginary in this sense just means opposite of real, so not real, imaginary, but it does exist. So whenever we have a situation like this, where the parabola opens up, but the vertex is above the x-axis, or the parabola opens down and the vertex is below the x-axis, we won't have any x-intercepts. And when we try to solve, we'll get something that has an imaginary complex solution. All right, let's go ahead and take a look now at problem 9. The first part is find the vertex in the axis of symmetry. So go ahead, pause the video, work that out as we've done many times, and turn the video back on and we'll do the x-intercepts together. So I chose this time to do completing the square. A was 1, so when I factored it out, it did not change the coefficients on the x squared or the x term. That makes b over a of 4, so half of it is 2, and when I squared it, I got 4. So I added and subtracted that value. And then I factored the trinomial part, bounced out the compensating term, combined everything. Remember to take the opposite of what's sitting next to x because it's close to that variable. So I got -2 for the x coordinate of the vertex and -5 for the y coordinate of the vertex. Then the line of symmetry or axis of symmetry is x equal h. So in this case, it's x equal -2. So far, so good. Now what we want are the x-intercepts. Now it turns out that it's easier to find the x-intercepts from general form because if we want to factor or use the quadratic property or quadratic formula, it's easier in that form. On the other hand, you can also use the square root property and you can do it from the vertex form. So I'll show you both methods, one starting from general form and one starting from the vertex form. Okay, so we're going to start again at x squared plus 4x minus 1. I'm going to write this in gray. So starting up here, I have f of x equal x squared plus 4x minus 1. I'm looking for the x-intercepts. Now, if I'm looking for x-intercepts, the opposite team got the ball, so y equals 0. So this tells me that the function notation becomes 0. So I actually end up with x squared plus 4x minus 1 equals 0. Now, if it bothers you to have the equals 0 on the left, you can just move it to the right. Now, again, a is +1, b is 4, and c is a -1. Now, looking at this one, I don't think it factors, right? The only factors of -1 are 1 and -1. I don't think there's any way that that's going to give me a 4 in the middle. So quadratic formula is necessary here. So now I'm going to use the quadratic formula, opposite of b plus or minus the square root of b squared minus 4ac, where each term is divided by 2a. And if you're looking at this, does that opposite of b over 2a look familiar? Yes. It is the x coordinate of the vertex, all right? It's actually hidden there in the quadratic formula. So now I'm going to go ahead and plug in these values and see what I come up with. So this is going to give me the opposite of 4 is -4 over 2 times 1. And I like to keep my terms separate. And this is going to square the 4 first, then -4 times a, which is 1, times c, which is -1. There is one place where even all these many decades later after learning it, I don't skip steps. Because if I mess up the sign here, I've tanked the whole problem. And that's the 4ac. Write it out. Don't mess up those signs. So this gives me -4 over 2, which is going to give me a 2, plus or minus, square root. 4 squared gives me 16. Now do the signs. Positive or a negative times a positive times a negative is a positive. All right, so I have a positive, and that's going to give me a 4, all divided by 2. Now I have to add the 16 and 4 first. So I get 2 plus or minus the square root of 20 divided by 2. Remember that you can write that as 4 times 5. because 4 is a perfect square. So we have 4 times 5. I mean, I could write it as 2 times 10, but it's not helpful. And then I can split it into the square root of 4 times the square root of 5. Only split across multiplication and division, never addition or subtraction. So the radical will split across the multiplication, not addition or subtraction. And when I am done writing everything out very carefully step by step, this will give me a 2 plus, oh, lost my minus somewhere, plus or minus 2 square roots of 5 over 2. Now these 2's will cancel, and I get 2 plus or minus, where do my minuses keep going? The square root of 5. All right, now that's not actually the x-intercept. That is the x-coordinate of the x-intercept, but it's not actually the x-intercept. The x-intercepts, there are 2 of them. 2 plus the square root of 5 comma 0, and 2 minus the square root of 5 comma 0, right? Now, I said that there's another way of doing this. You can do this using the factored form, the vertex form. So we're going to come up here to this line right here, and we're going to do the same process again, and I'm going to choose a different color. So I'm going to kind of line this off a little bit. Hopefully I have enough space. So I've got f of x equal to 1 times x plus 2 quantity squared minus 5. Okay, well, first off, I'm looking for x-intercept. So y is 0. So I know this gives me 0 equal 1 times x plus 2 quantity squared minus 5. Now, I can go ahead and move the 5. I want to isolate x. But to get to x, I have to undo the order of operation in reverse order. So I've got to pull the 5 away first by adding 5 to both sides of the equation. That's balanced at the equal sign. So I get 5 equals, and that 1 times isn't going to change anything, but I'm going to keep the 1 there so that you know what to do in case it's not a 1. Now, the next thing I would do would be to move a if a were not a 1. So the next thing I would do would be to divide both sides by the 1 to, quote, move it to the other side. But I don't really need to do that because 1 times anything doesn't change it. So now I've isolated the binomial square. So now what I have is something squared is 5. So I want to undo that by taking the square root of both sides, and that will give me a plus or minus. So this is going to give me plus or minus the square root of 5 equal to the square root of x plus 2 quantity squared. And when you take the square root of something squared, you get the thing. So this is going to give me x plus 2. We've compensated for not knowing whether it was positive or negative by putting the plus or minus on the other side. And this gives me x plus 2 equals plus or minus the square root of 5. And then I can solve for x by subtracting the 2. And remember that I can't combine those because they're different numbers. Something has gone awry. I lost a negative. All right, how did I know something was wrong? This gave me a negative 2, and over here I had positive 2. So I knew something was wrong. And when I look back, I can see I lost my negative right there. So all of these should be negative coming down to the end. Let's get that fixed. And continuing with this part, I get negative 2 plus or minus the square root of 5. Now, again, that's not actually the x-intercepts, it's the x-coordinates of the x-intercept. I have to write the intercepts in this form right here. This is what the intercepts are. They're ordered pairs, right? So we need to write them in ordered pair form. Let's move on now to the next problem. So this problem is exactly like the last one. They want us to find the vertex, the line of symmetry, and the x-intercepts. So because we've demonstrated that technique, I want you to pause the video, go work it out, then turn the video back on and we'll compare our answers. And I'll be sure not to mess it up this time. So let's see how we compare when we look at our answers. This one was going to be more difficult to do by completing the square, so I did it that way because I want you to see what happens when the b is not divisible by a. You get fractions and there's no way around it. You're going to have to work with them. So in this case, when I factored out the 2, it left 7 halves for the value of b over a. When I take half of that, it multiplies the denominator by 2, so I get 7 over 4. Now, this number is going to be what shows up inside the binomial square. But to figure out how to force that to happen, I have to square that half of b over a, and I got 49 over 16. So I add that and subtract it. Now, the first 3 terms I factor as this perfect square trinomial becomes a binomial squared. And then I bounce out the compensating term, which is going to give me, oops, and I've already got a mistake. So let me fix that, and then I'll be right back. I seem to have a problem with losing negatives today, so I'll have to be more careful. So when I do this right here and I bounce out the term, I get a negative 49 over 8. And then when I combine that, notice I have to get a common denominator. So I write one as 8 over 8. And then I subtract the 2 together, and that gives me negative 57 over 8. That means the vertex is negative 7/4 negative 57 over 8, which is a nasty number. But it is the vertex. And the line of symmetry is the x coordinate of the vertex, x equal negative 7 over 4. It's that vertical line. So let's take a look at the graph over here. You can see the graph right here. And this point right down here at the bottom, if I can get it right on the bottom, that seems to be it. That is negative 7/4, whatever that other thing was, negative 57 over 8. So that gives us those decimal numbers exactly. Now we're looking to see where it crosses the x-axis, and you can see it crosses here and here. But unfortunately, Desmos will not give us the exact value. If we enter the exact value, which you can see I have done here, it will, however, let you label those 2 spots. So you can tell that it's that one. If I change it to an x, you can see the x showing up right there on top of that x-intercept. And if I make this green one an x as well, you can see it showing up right here. So how did I get the x-intercepts? Again, I can take it in the vertex form, and I can set it equal to 0. The x-intercept y is 0. And then I simply isolate x, first by moving the negative 57/8 to the opposite side, and then by getting rid of a. So to get rid of the 2, I had to multiply by 1/2 on both sides, which gave me 57 over 16. Then I take the square root of both sides. The side with the variable does not get a plus or minus, but the side across from it does, because we don't know anything about x. So the side without the x gets the plus or minus. Remember that you can split radicals across multiplication and division. So that gives me square root of 57 over 4. Now 57 does factor. It's 3 times 19. But 3 and 19 are both prime. They're not perfect squares. So factoring it won't help. And then you can see that I wrote out the x-intercepts right here. Let's now take a look at the next problem in our problem list. Now, in our next problem, problem number 11, we're actually given a graphed function, and we're asked to write the equation of the parabola, write the equation of the quadratic function. Now, when we're looking at this, there are different ways of doing it, and they're all perfectly valid and all good. So there's more than one way to get an equation for this one. When we're looking at this, notice first off that the vertex appears to be right here in between. And I can be sure that that's the vertex because it's definitely going through negative 2, 0 and 2, 0. So I know that the line of symmetry has to be halfway between negative 2 and 2, or at x equals 0. And then it looks like the y value here is negative 4. So the first thing it looks like I know for sure is that the vertex is equal to 0, negative 4. So that means h is 0 and k equals a -4. So if I want to put it into the vertex form or the standard form, then I have f of x equals some unknown a times x minus 0 quantity squared minus 4. Okay, so far so good. All right, well, I know x minus 0 is just x, so I can write this as ax squared minus 4. Now I've got to find at least one exact point on the parabola, but I've actually got two. It goes through both 2, 0 and -2, 0. It also looks like it goes through one of these other points up here, but for sure it's going through those two. It also looks like it goes through 1, -3 and -1, -3. But for sure it's crossing at 2, 0 and -2, 0. So I'm going to use the easier of those 2 points. I'm going to use 2, 0. You can use any point as long as it goes through exactly. So now I know that when x is 2, y should be 0, but y is the f of x. So I get 0 equals a times 2 quantity squared minus 4. And this is going to give me 0 equals 4a minus 4. And solving for a, I find that a, of course, has to be 1. There's no other way to do it. And that tells me that I can write the equation then as 1x squared minus 4. And that becomes the equation that we're looking for. So let's take a look at the next problem, which is probably relatively similar. So here is our next problem. If I can get it to go, it's kind of going slow. So we see this one is a downward opening parabola. So let's copy this off a little bit, and then we'll work on this problem. So you may want to go ahead and work on it. It looks like the vertex is here at -3, 1. Now it looks like it's going through the x-axis at -4, 0 and -2, 0. So those give you points that you could use. It also looks like it goes through 0, -8. You could use that as well. So it just depends on which point you see and which one you want to use. So go ahead, pause the video, work out which one it is, and then come back and we'll compare answers. Okay, so on this particular problem, I wrote the vertex, -3, 1, put it into the formula for the vertex form. Note that this gives me a double negative, so it actually becomes x plus 3 quantity squared plus 1. And don't forget, you've got to have a here. Now, I chose to use the point 0, -8 just to do something a little different. You could have used one of the x-intercepts. Doesn't matter as long as it's exact. So this means that when x is 0, y is -8. So plugging that into the equation and solving, I got a is -1. Now, I would take this answer right here. This would be okay for me on an exam. But if it wants general form, then you'd have to multiply this out by squaring first, then distributing the negative, then combining the like constants. And you would end up with this form that you see down here. Let's move on to the next problem. So on this problem, we're asked to find the domain and range for a quadratic function with a vertex of 0, 5 if the graph opens down. So it's like a downward opening parabola. Now, when we're doing this, again, the easiest thing to do is sketch it first. So, okay, I've got my XY axis here. And 0, 5, 2, 3, 4, 5 would be here. And I know it opens down somehow. I don't know where, but I do know it has to cross the x-axis. There have to be x-intercepts. But this isn't asking me for that. It's just asking for domain and range. Well, the domain of all up and down opening parabolas is all real. So I already know that part. It's going to be -infinity to infinity. What about the range? Well, the range is going to be negative numbers all the way up to 0, and then from 0 to 5. So the largest number is 5, and that puts it on the right. So I'm going to have something coming up here and stopping at 5 with a square bracket. And the only thing to the left has got to be negative infinity. So we have negative infinity up to 5 closed. Let's take a look at the next one. So for one of our last two problems, we now have a word problem. You know, word problems are more difficult. They take more time. The key is to draw a picture. A picture is worth so much. It also tells the instructor what you're thinking. If your picture is wrong, it's almost certainly going to be wrong. But it does at least let the instructor know what you were thinking. So let's read through it first. First time we read through, we're just getting a vague idea of what we're talking about. Then we'll go back and we'll pull it apart about every 2 to 3 words and translate the mathematics from the English. So the first time we read, just straight through. Find the dimensions of a rectangular corral split into 2 pins of the same size, producing the greatest possible enclosed area given 300 feet of fencing. Well, it doesn't have anything to do with money. Okay, I know that. And it doesn't have anything to do with triangles or circles. So I don't need any of those formulas. But it did mention a rectangle. And it also talked about a greatest possible area. And we've been studying quadratic functions. We're going to get a quadratic equation. And the greatest possible whatever is going to occur at the vertex, the y-coordinate of the vertex. So what we need to do is draw a picture. So we're going to go back to the beginning and we're going to pull it apart. And as we pull it apart, we're going to draw a picture. Find the dimensions. Okay, so I'm looking for the size of something, of a rectangular corral. Okay, so first thing I'm going to draw is a rectangular corral. Okay, so I've got my rectangular corral. So it says the rectangular corral is split. Okay, it's divided into 2 pins of the same size. Oh, well, then I'm going to have to split it down the middle. That doesn't necessarily mean they're going to be squares. They could both be rectangles, right? I mean, if it's shaped like this and I divide it in half, well, they're definitely not squares, right? So I got this. And now it says producing the greatest possible enclosed area given 300 feet of fencing. Okay. I got to go back to the beginning again. Find the dimensions. Oh, it wants the length and width of this rectangular corral. Well, then I need to call it something. So if I call this distance right here y, then that's also got to be a y, and that's got to be a y. I could call this x, but then since I split it into pins of the same size, each one individually would be half of x. And I don't want to deal with fractions. So I'm actually going to make this right here be x, which means that the whole side is 2x, because this is also going to be an x. So find the dimensions. Okay, well, according to my picture, my width is, I guess my width is y. Okay, so my width is going to be y, and my length is actually 2x, right? So now I know what the dimensions should be of a rectangular corral. Yeah, I've taken care of that. Split into 2 pins, yep, of the same size, yes. By setting this to be x and this to be x, then they're both x by y, right? Of the same size, producing the greatest possible enclosed area. Okay, so greatest possible enclosed area, okay. Given 300 feet of fencing. Well, I don't have area yet. My area is going to have to be, well, what would the area of one of them be? Well, the area of one would be x times y, and I've got 2 of them, so that would be 2xy. Or I could look at the whole big rectangle and say 2x long by y wide. So the area of the whole thing is 2xy. Okay. All right, I got that down. So I've used every word except the 300 feet of fencing. I haven't used that yet. Well, let me go ahead and label the rest of these sides because I know that this side is also x and this side is also x. 300 feet of fencing. Well, the outsides here, let me outline them in yellow. This is my fencing. And I've got 300 feet of fence. I want to use it all because I want the area to be as big as possible. Okay. Well, then that means that if I add up all these distances, all these side lengths, that should add up to 300. Yeah? Okay, well, let's do that. We'll start up here in the upper left. So I have x plus another x plus a y plus an x plus another x plus a y, and don't forget about the y in the middle, plus another y has to be 300 feet of fencing. Well, that's 1, 2, 3, 4 x's and 3 y's. Yeah, that matches my picture. 4x plus 3y equals 300. Okay. Well, I know that I want to maximize area, right? I want the area to be as big as possible. So somehow I've got to turn this into a quadratic equation. But I also have to use this equation because this tells me how much fencing I've got to use. So, well, let's solve for x, but we could solve for y too. Which would you rather do, x or y? Doesn't matter? No, it doesn't matter. Well, let's just solve for x and see what we get. All right, so I'm going to solve for x from this one. This is going to give me 4x equals 300 minus 3y, right? Subtract the 3y from both sides. Now divide everything by 4. Okay, so 4x divided by 4 equals 300 divided by 4 minus 3 divided by 4y. So x equals, what's 300 divided by 4? 75? I think that's right. So you guys check me. We have 75 minus 3/4 y. And that's going to be x. But I could take this and I could substitute it in up here. So now going on to the next page, yeah, these are 2-pagers. I know that the area, which is the thing I'm trying to make as big as possible, maximize it, is going to be 2 times this expression, because it's replacing the x, 75 minus 3 over 4y. Oh, times another y, right? Because this is my 2xy. Yeah, that works. Okay. So this is my area function. So now let's go ahead and multiply it out. So this will give me 150. And then the 2 and the 4 would reduce. So I would still have minus 3 halves. And what about this y at the back? Well, I haven't distributed the y yet. So let's distribute. It looks weird at the back, but it works. It's the same thing. So it's going to give me 150y minus 3 halves y squared. Aha. All right. Now what? Okay. Well, it's quadratic in y, right? And where does the maximum area occur? Vertex. So let's go get the coordinates of the vertex. So let's find this y at the vertex. So when I do that, what am I going to get? So go ahead and pause the video, find the vertex, and then turn the video back on and we'll compare. Okay, so this time I chose to use the formula. Now be careful because this isn't written in the normal ax squared plus bx plus c format. Notice that the squared term, the coefficient, is always a. So a is negative 3 halves, And the variable term, the coefficient is always b. So b is 150. We don't have a c. So then I used the formula and I ended up getting that y is 50. Well, now that gives me part of what I needed. I know now that the width is going to be 50, but I need the length. And the length is 2x, and I only have y. Okay, I only have y. Well, I have an expression for x. It's right here. X is 75 minus 3/4 of y. So coming down here, I also know that x is 75 minus 3/4 times y. And I know my y is 50, so I have 75 minus 3/4 times 50. Now, that's going to not be a pleasant fraction, but basically 50 divided by 4 is 12.5. But I'm just going to go ahead and reduce it by half. So I get 25 over 2 times the 3, which gives me 75 over 2, I believe. So this gives me minus 75 over 2. And then I can get a common denominator, which is 2, and this gives me 150 over 2 minus 75 over 2, which tells me that x has to be 75 over 2. And that gives me the other when I take into account that I'm not looking for x, for 2x. So since x was 75 over 2, then 2x is 75, and my width y was 50. So 50 by 75, if I make that the size of the large rectangle, then I can maximize the area. Now that sounds crazy, but that's exactly how you can find that problem out. We have one more problem to do. Let's take a look at it. So this is the last problem in our homework set. It's another word problem. And remember, to do word problems, you read through one time, just get a vague idea what kinds of formulas might be important and which ones aren't, right? And then you pull it apart by reading it about every 2 to 3 words. You're looking for parts of speech: subject phrase, verb phrase, prepositional phrase, subordinate clauses, punctuation. That's what you're looking for, all right? And for those of you where grammar's not your thing, about every 2 to 3 words, you're going to stop and write something down. But first, we read it one time through. A ball is thrown in the air from the top of a building. Its height in meters above the ground as a function of time in seconds is given by h of t equals negative 4.9 t squared plus 16t plus 14. How many seconds does it take to reach maximum height? Enter the answer with at least 3 decimal places. Okay, so how long does it take to reach maximum height? Okay, well, it's got nothing to do with distance, rate, time. I'm throwing a ball up in the air from on top of a building, which is kind of a weird thing to do, but okay. It doesn't seem to have anything to do with rectangles, circles, triangles, nothing like that. So let's go back to the beginning and let's sketch a picture. A ball, got it, is thrown, got it, in the air. Where else would you throw it? From the top of a building. About every 2 to 3 words. Okay, so the first thing I need to do is draw the top of my building. Here's the ground, and I've got a tree over here. All right, so here's me, stick figure, sitting here, and I throw a ball. And what's the ball going to do? The ball's going to go up in the air, and then it's going to come down like this, all right? So at some point, it's going to reach its maximum height, which is right there. Okay, so I know that this is what the ball is going to do. Okay, first sentence, I got it. Its height, okay, in meters above the ground, okay, so not from the roof of the building, but from the ground, as a function of time in seconds is given by this equation. How many seconds does it take to reach maximum height? Well, t is time and h is the height. And gosh, this looks a lot like a parabola. Yeah, it is. And this is a parabola. And where do I find a maximum? At the vertex, where I always find my maximums or minimums. So let's go ahead and take this equation and find the coordinates of the vertex. Pause the video, figure it out, turn it back on, and let's compare. So let's see how you did. I chose to do this one again using the formula because the numbers are kind of nasty. Completing the square would just not be good. The numbers are going to be nasty no matter what we do. So I did negative b over 2a, and I got 8 divided by 4.9, which is the same as 80 divided by 49. I'm multiplying top and bottom by 10, which of course 10 over 10 is 1, so I'm allowed to do that. So I got 80 over 49. Now, if I write this out as a decimal, this is approximately 1.63, well, it says, let's go a little further, 265. And then, I mean, it doesn't stop, it keeps going. All right, so when we're looking at that, this, of course, is going to be the time, the x coordinate is actually t. This is going to be the time where it reaches the top and comes back down. So this is actually what they're looking for. I'm actually done. It's 80 over 49 or 1.63265, blah, blah, blah. Now, how high above the building is it? So the maximum isn't the when it occurs, it's the actual height above the whatever. So when I do that and I plug it into the equation, I end up with about 27.06, really close to 27, which means this can't be a very tall building. My picture's way off to scale because this is 27 well, I don't know, 27 meters. Yeah, okay, I take it back. It's pretty tall. I was thinking feet at first. 27 meters from the ground. All right, so this is 27 meters, it's close to 30. So yeah, it's whopping large, right? A meter is about 3 feet, so under 900 feet or whatever, but still very, very tall. So I hope this helps you to do your homework, and I hope you'll join me for the next video in the sequence.